Hey, before I do example 2, let me just walk you through this process I printed out for you. Read the problem carefully. That's step 1 of the word problem, and I mean, by this time you guys are calculus students, you should know you're supposed to read the word problem carefully. Read the word problem carefully. Identify what variables are necessary, and you want the minimum number of variables possible. All right? If there's a way to make one variable the same as the other, like for example, if they say the length is twice the width, that's one variable to represent length and width. All right, so you don't have to use L for length and W for width. Length, let's say W's width, then 2W would be length. So if they give you some type of a statement along those lines, you want the minimum number of variables possible. Every time you pick one less variable, you've made the problem about 15 times easier. Those aren't exact facts there. 17% of statistics are made up on the spot. That was one of them. All right. The 17% was another. But anyway, minimum number of variables possible. Draw a figure if applicable. Okay. If it's talking about numbers, there was no figure applicable on the last one problem, right? I didn't need to draw a figure to represent the product of these numbers. We're not in 2nd grade. All right. But keep in mind, if there's a figure, if they're talking about surface area, volume, area, perimeter, that kind of stuff, drawing a picture sometimes is helpful, all right, and worth doing, all right? Set up an equation involving whatever's being held constant using all necessary variables, all right? So the last problem, the difference in the two numbers was 100, right? That was, we had to write out that equation representing those unknowns in an equation. Every variable that you need to use in the problem needs to be used in this equation. All right. Use that equation to put one variable in terms of the other. So, like I got x equals something about y, right? So do that. The purpose of that fact is to be able to change one variable into another variable to limit the number of variables. And whatever you're trying to optimize is going to be the key. Okay. So if it says optimize surface area, write out a surface area formula using the variables that you've established that need to be used. Optimize volume, do that. Optimize cost, do that. Whatever that you're trying to optimize, get an equation involving that equal to all the variables you're going to be using. Do a quick substitution from number 4 to get one of the variables out of the problem. Then do your derivative, test the intervals, and answer the question. The question is usually find the minimum cost, find the maximum volume, that kind of stuff. Right? So, example 2, we're just going to go through this process here step by step. Number 1, read the problem carefully. Farmer with 1,200 feet of fencing wants to enclose a rectangular area and then divide it into 5 pens with fencing parallel to one side of the rectangle. You might need to read that several times to understand what they're talking about. So we have a rectangular area, right? We want 5 pens fencing parallel to one side. So let's say that we have these sides here, right? So put fences along this way here to create 5 different pens. So in my thoughts, that's what it's going to look like. All right? And again, they use wording like that sometimes. So sometimes you have to read it 2 or 3 times to get a real good picture of what it is they want you to draw. All right? But that's how they're trying to subdivide this rectangular area. What is the largest possible total area for the 5 pens? So let's just take a look at a couple of specific things that happen in this problem that are going to be happening in all these problems, these optimization problems. First thing, seems very benign, but it says 1,200 feet of fencing. If I'm the farmer and I want my pen to look like that, every one of those black lines represents fence, right? So every one of those black lines is using up fencing. All right? That represents the fact that they're telling me, and that's what I'm going to want to do for step number 3, I believe. Set up an equation involving whatever's being held constant, okay? All the farmer has is 1,200 feet of fencing. That's his materials. That's what he has to work with, all right? He's going to use it all because he's very efficient, all right? He's a good farmer. He knows how to use all of his materials. He's not going to have 500 feet of fencing laying over there. We don't need that. Made it too small, that's okay. I don't want to redo it. All right, he's very efficient. Okay, I've got one length going this way and one length going that way. That's a total of 2 things that we don't know. Even though there's 1, 2, 3, 4, 5, 6 pieces and 2 pieces, all these are the same, both of those are the same. So if I call this X and call this X, and I call that Y and 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 that Y, I've used the minimum number of variables possible to represent the things I don't know in this picture. Okay, so again, that's within the step 1 idea. You want to minimize the number of variables. There's 6 things I don't know, actually 8 things I don't know there, but 6 of them are the same and 2 of them are the same. So I can use 2 variables to represent everything I don't know. The 1,200 feet of fencing simply tells me that if I add up all this stuff, it's going to be 1,200, right? So there's 2 x's and there's 6 y's to make a total of 1,200 feet of fencing. This doesn't happen always, but notice 2, 6, and 1,200 all divided by 2. That is legal, you can do it. So x plus 3y is equal to 600 is also true. Numbers are smaller, so it's easier. All right. What I want to do then is I want to solve that for x or y, which is easier. Solve for x, right? Because there's no division necessary. So if I move the 3y over there, I'm going to get x is equal to 600 minus 3y. Okay. That represents a part that you're going to get to in almost every one of these problems. Some variable equals some expression about the other variable. All right. Important, but not yet. Okay. Next thing you want to worry about: what are you trying to optimize here? What is the largest possible total area for the 5 pins? We're trying to find the area of this thing, right? All right. What's the area formula for this picture? Length times width, which we're using x and y to represent those, right? Yeah. Okay. Now, I can find the area of each individual pen and add them up, right? Let's just say they're all equal, so 1/5 x, 1/5 x, 1/5 x, 1/5 x, 1/5 x, all multiplied by y, add them up, you're going to get x, y anyway. But the entire area of everything is the entire length times the entire width, x times y, is the area of the pens. That is step 5, and that is a very important step. It needs to be done appropriately and correctly. What you're trying to optimize related to every single variable you see over in that picture. All right? Then, once you get that, now we're going to use our substitution. Change x to 600 minus 3y, so a equals 600 minus 3y times y. So a is equal to 600y minus 3y squared. And just like that, we've gone from a 3-variable expression or equation here into a 2-variable equation. 2-variable equations are your best friend. Once you get to there and you're in your optimizing equation here and you got a 2-variable equation, you're ready to go every time. If you ever have to do it with 3 variables, yeah, it'll be very unpleasant. So I would expect this is going to be a point we get to every single time. A prime is equal to 600 minus 6y. And if a prime is 600 minus 6y, again, there's no end. Well, there's no endpoints really. We kind of are limited, right? Because x or y can't even be bigger than 1,200. But as long as we'll just pretend endpoints don't exist in this one. Undefined doesn't exist because it's polynomial, so just equals 0. It's almost always just equals 0 get you what you're looking for. So 600 equals 6y. Y is equal to 100. All right. Now, if you only get one critical number, chances are that's what you're looking for. But just to verify, just to be safe, if I go from negative infinity to 100, and then from 100 to infinity, let's go 1 and 200. 6 times 1 is 6. 600 minus 6 is positive something. 6 times 200 is 1,200. 600 minus 1,200 is negative 600. So it increases, then it decreases at a critical number, which means the critical number is a maximum. We're trying to find the largest, which is a maximum. So that verifies that we found what we're looking for, right? All right. All we found was y, so we have to find x also. X equals 600 minus 3y. 3 times 100 is 300, so x equals 300. What unit are x and y? Feet. Feet, very good. So 100 feet for y, 300 feet for x. Does that answer the question? No. No. It wants to know the actual area, right? What is the largest possible total area? So some of the things they ask, all right, they could ask that. They could say, what are the dimensions that create the maximum area? That could be another question. They say, what are the dimensions? We want the longer side to be 300. We want the shorter side to be 100. If you've drawn me a picture and established what it looks like, If you just put x equals 300, y equals 100, that's fine. If you didn't draw this picture on your paper and you want to describe that, you'd have to say, well, you have to make the sides that don't have the parallel fencing all 300, and the ones where all the 5 parallel sides have to be 100. It have to be a little more wordy. Okay, picture's worth 1,000 words. You draw me a picture, you show me what x and y represent, tell me what x and y equal, you give me the dimensions, that's fine. Right? The area, though, is just x times y, so if we do 300 times 100, we get the area to be 30,000, right? What unit goes on that?
Feet squared.
Feet squared, very good. So area is going to be square units. So that answers the question they're asking. And again, that's kind of what you need to look at each time. And that is an optimization problem. Pretty straightforward one. It's pretty classic. A lot of times the farmer wants to build a thing next to a river, so you don't need a fence on the riverside. They do that sometimes too, so just keep that in mind. So read it carefully, draw an appropriate picture for the problem. Everything else is just good geometry stuff.